Morning all. Today we are going to see the grid world problem, which is for iterative policy evaluation in small grid world under the course reinforcement learning. So I thank to my guru Shashi sir, and the slides are prepared by referring the book Reinforcement Learning, an Introduction, the second edition by Sutton and Bott. So in the iterative policy evaluation, we are considered the small grid world where we are going to consider a grid world of size 4 cross 4, which are going to have the states total 16. Out of the 16 states, two states we are considering as the terminal state. So this is one terminal state and this is the second terminal state. And the remaining 14 states we can have where these are non-terminal states. And the actions which we can consider is either moving in upside or downside or right side or left side. So these are the four actions we are going to be considered. And in all these states, except the terminal state, for all the transitions, the reward we are going to be considered is -1. So that non-terminal states set S is equivalent to the states from S1, S2, S3 until S4. And there are four actions possible in each state. So the set of actions are up, down, right, and left, which deterministically cause the corresponding state transition, except that actions that would take the agent of the grid, in fact, leave the state unchanged. This is undiscounted episodic task, and the reward we are going to be considered is -1 on all the transitions until the terminal state is reached. The terminal state is shaded in the figure. The accepted reward function is for the reward is -1 for the transition from any S0 state to for action A, change of the state is S. For all the states S, S0 and actions A. The small grid world we are representing as a finite MDP where the set of states we are going to be considered as S is equivalent to 1 to 14, and the next state, that is S plus, we are going to be considered apart from these 14 states, we are also considering two more states which are terminal states. So this is a terminal state. So in our example, we are considering two terminal states. So in total, we are going to have 16 states. The reward is -1 for all the states. So for a state which is a member of S and the actions which is a set of the actions which we are going to be considering is left, up, right and down. Next we are going to be consider the MDP, the probability of transition from the state S to S dash for a given action depending upon the policy and a reward R. So the state transition when on the edge stay on the current cell, otherwise move to the direction specified by the action. So if any state is on the boundary and we don't have any state to move any one of these actions, then we are going to be fall into the current cell. Otherwise, we are going to be moved to the specific direction. We will see in detail. Let us assume if I have S5 state, for this S5 state on left hand side, we are going to have S4 state. On the top, we are going to have S1 state, and on the downside S9 state. On right hand side, we are going to have S6 state. So now if we are in S5 state, when the action is upward, we are going to move to S1 state. And if we are in S5 state and the action if you are taken is downside, then we are going to move to the S9 state. And if you are in S5 state and the action if you are taken as towards left side, that is action is left, then we are moving to S4 state. And whenever we are in S5 state and if the action is on right hand side, we are going to move into S6. Suppose if we have S2 state, for S2 state on left hand side we have S1 state, on right hand side we have S3 state, on downside we have S6 state. So if your current state is S2, for left side we are going to be have the transition to S1 state, for right side we have the transition to S3 state, for downside we have S6 state, but for upward we don't have any more state we are defined here, so this will be fall to the same transition, that is this term specifies. Here we are going to be consider the reward is -1 unless the state of transition is terminal state. For all the remaining state, if the state is moving from S1 to S14, we are going to be consider the state transitions are with the transition reward is equal to -1. As per problem statement, it is undiscounted episodic MDP, and the discount factor we are going to be consider is gamma is equivalent to 1, and all the four actions are having the equal probability. So the actions we are going to have four actions. So the probability for a left side movement is 1 by 4. For right side, the probability of transition is 1 by 4. For upside, the transition is 1 by 4. On downside, the probability transition is 1 by 4. So as all these actions are equally probable, we are going to be consider the transition or the policy probability is equivalent to 0.25. Now for considering the evaluation of V till the optimal value function V pi, we are going to consider or we are going to calculate the value function V pi for equal probable random policy, where the policy pi for action A from state S will have the probability is equivalent to 1 by 4, which is nothing but 0.25. The value function for each transition is calculated by whenever you are changing for K plus 1 state for S, which is going to give the expected value of R of t plus 1 gamma times of Vk Sd plus 1 for a state the current at time t, the current state is S. This expected function we can write as the summation for all actions, the probability of actions for a particular state, that is phi of A by S, and the summation of the transition from S to S dash probability for a given action A with a reward of R, R plus gamma times of Vk S dash. So in all these cases, for action we are going to be consider the probability is 1 by 4, whereas the transition from S to S dash we are going to be consider the probability is equivalent to 1. Now we will start the evaluation of value function, that is V of S, for each and every state. So we will take initially, we will consider all the states are having the value function is equivalent to 0, as we are going to have total 16 states, which are states are V0, V1, V2, V3, V4, V5, V6, V7, V8, V9, V10, V11, V12, V13, V14, V15. We will initialize all these initial value for the value function is equivalent to 0. So for V0, 0, for V1, 0, V2, 0, V3, V4, V5, V6, V7, V8, V9, V10, V11, V12, V13, V14, V15, 0. The value function for the terminal state. So what are the terminal state we are going to be considered as? The terminal states are V0 and V15. The value function for these two states, that is terminal state, which is always is 0. So we are going to evaluate V1 to V14. The terminal state already we will consider. We said the value we are going to consider the value function is equivalent to 0. Now we will start evaluating the value function for V1. So we will write the k plus 1 as V1. So V1 of S is equivalent to the sum of all the actions. Now how many actions we are going to have? 4 actions. So pi of A by S, summation S dash comma R, the probability of transition to S dash from A for action A with a reward of R, reward plus gamma, that is discount factor, the previous state. So now in this case, as k plus 1 is equivalent to 1, so k we are going to be considered as 0 of S dash. Now coming to the state V1. If you observe for V1 state, we are going to move to V0 state for left action. For right action, the transition is for V2. For downside, the transition is for V5. For V1, we don't have upward direction, so we are going to be fall into the same. So that we can write as summation. So pi. So what are the various policies we are going to have? We are going to be considered total 4 policies. One is for the transition for actions. What are the actions we can have? Either you can have towards left side or toward right side, upward direction, downward direction. For any given state S, summation S dash comma R, the probability always we are going to be considered as 1. So this you will write as 1. And the reward is -1 always, plus the gamma, the discount factor is 1, multiply with the previous state values for each and every transition. Now if you observe, for left action, we are going to be transit to V0 state. For right action, we are going to be transition to V2 state. For upward, we are going to be retained in the same state, V1. For downside, we are going to have the transition for V5. So now we will write as first left side I will take. So the probability of policy for taking an action towards the left side. Now we are in the state is S1, right? So this summation we are going to take for all the 4 cases. So one is minus 1 plus when now we are going for left side, what is the transition we are going to have towards a V0 state, that is S0 we can take. So this is S0 state, this is S2 state, S1 state and S1 state. 1 plus 1 into a V0 of, for left side, what is the value we are going to have? A V0. This is for action towards left side plus the probability of action towards a right side when we are in the state S1, the reward is minus 1 plus the previous value, that is V0 for what is the state for right side. So whenever we have a transition towards right side, the state is S2. So we have to substitute the VS2 value plus phi of the next action we can have towards upside from S1 state with a reward of V1, the previous state value, that is V0, for which state whenever we go for in the upward direction, as we are not having any state on the upward side, we are going to be fall into the same state. So that is S1 plus phi of the next action we can have is downside for S1 state minus 1 plus V0 of. So when we go towards downside action, the next state is equivalent to V5. The state is S5. So V0 of S5. Substituting the value, as we have considered, for each and every action, it is a equal probability, that is equivalent to 0.25 times of minus 1 plus the initial value we have considered for all the states are a 0. So we take as 0 plus the probability towards right side is 0.25 minus 1 plus 0 plus 0.25 minus 1 plus 0 plus 0.25. So for downside, the probability is 0.25 minus 1 plus 0. So which is going to give as 0.25 if you take as common. So left out is minus 1, minus 1, minus 1, minus 1, which is going to have the value is equivalent to 0.25 into minus 4, which we are going to get as minus 1. So this is the V1 of S, where we are going to have the previous value is 0. That now it was changed to minus 1. Similarly, we are going to calculate for the remaining states also, that is from S2 states to S15 state. However, S15 is 0, so we will calculate only up to S14. Now, our current state we are going to be considered is for S2 state. Now, if you observe for S2 state, if the action is towards the left side, the change of state is towards S1. If the action is towards a right side, if the action is right side, the state will be transit to S3 state. If it is a downside, the state changes to S6. For upward, we don't have any action, so it is going to be fall for to the same state. Now we will write the function for value function for V2 of S. What is the state we are going to consider is, this is first iteration only. So this is V1 for the state is S2, for the state is S2, which you will write as summation of all the actions. What are the actions we are going to consider? This is left, right, up and down. Summation S dash to R. We have considered, assume all the probabilities for the transition is 1, and the reward for all the transitions except the terminal state -1 plus discount factor is 1, Vk. As k plus 1 is 1, we are going to be consider the initial value for the new state. So now the current transition we are taking with respect to S2. Now we will expand. First I will consider for left side. So for y left side for S2 -1 plus V0 of. So for left side, what is the transition? What is the state we are going to have? S1. So V0 of S1 plus phi of the action is towards right side from the state S2. The reward is -1. The previous value, that is V0, and the state we are going to have is S3. So that is S3 plus the next action is towards upside from the state S2. Reward is -1. The previous value we are going to consider as V0 of. As we don't have any state in the upward direction, we are going to be considered the same state, that is S2 only, plus phi of. So the action is downside in S2 state, multiply with the reward is -1 plus V0 of. So when we move towards downside, what is the state we are having? S6. As we know, the probability of all the actions is 0.25, multiply with -1 plus. For initially, we have considered V0 of for all the states as 0. So this we are going to be considered as 0 plus 0.25 into -1 plus 0 plus 0.25 into -1 plus 0 plus 0.25 into -1 into plus 0. So which is going to give as 0.25 and take as common factor. Left out is -1. Here also -1. Here also -1. The last one also -1. So which is going to give as 0.25 into -4, which it is going to return as -1. So now V1 of S2 is equivalent to -1. So here I'll take the state table values. The terminal states are always 0. Previously, we have calculated for S1 as -1, S2 also -1. Now we have to evaluate for remaining states also. Now we will move to the next state, that is S3. So we will write the value function, that is V1 for the state S3, which is going to give the summation of all the actions, that is phi of actions for the state S3, summation of the new state is we are going to take as S dash. For reward is always -1. The probability is 1. The reward is -1. The discount factor is 1. So V0 of what is the next state it is going to have the transition depending upon the actions. Now if you observe from S3 state, when we go or if you take the action towards left side, we are reaching to S2 state. We don't have any more state is existing on right hand side. So we are going to be fall into the same state, that is S3. In upward direction also we don't have any state. So this also we are going to be fall into the S3 state only. When we take the action towards downside, we are going to reach to S7 state. Now we will write the expansion. So here actions, what are the actions we are going to be considered? Left, right, upward and downward. So now we'll write the probability of left action from S3 state. The summation we are going to write as -1 plus V naught of what is the next state we are going to have when it is left side. So we are going to reach to S2 state plus the probability of action right from S3 state. The reward is -1 and V naught of which state we are going to consider. For S3 state, there is no state is existing on right hand side. So we are going to be fall into the same state, that is S3 plus the probability of action, that is upside from the state S3. Reward is -1. V naught of in upward we don't have any more state, so we are going to be fall into the same state, that is S3 plus the action towards downside from S3 state. Reward is -1 plus V naught of when we take a action towards downside, we are reaching to S7, so we have to take a V0 of S7. Now we'll take, as we know, the pi for all the actions is 0.25 or 1 by 4, anything you can take. So 0.25 into -1. What is V0 of S2? As we are concerned, the initial value for all the states as 0, we will take 0 for S2 state plus 0.25 into -1 plus 0 plus 0.25 into -1 plus 0 plus 0.25 into -1 plus 0. Now, if you take 0.25 as common factor, what is left out with? -1 plus 0, that is -1. Here also -1. Here also -1. Here also -1. So, which we are going to get as 0.25 into -4, which will give -1. Again, I am writing the new state values. So, terminal states are always 0. We already evaluated for S1 state, S2 state. Now we are going to be updated to S3 state. Now we will move to evaluating for S4 state. Now we will write the value function, that is V1 of S4. Now we are in S4 state. When we are in S4 state, if we take the action towards the left side, we don't have any state on left hand side. So we are going to be fall into the same state, that is S4. For right hand side, the transition is for S5 state. For upward side, we are going to have the transition is S0. For downside, the transition is for S6 state. Now we will write the summation of all the actions, the probability A of S, summation S dash for reward. The probability we are going to consider as 1 for all the transitions for any action. The reward is -1, discount factor is 1, V0 of the next state depending upon the action. That will take as S dash. So this we can expand as, so the various actions we can have is left, right, upward and downward side. So the probability of action towards left side from the state, now we are in S4 state. S4, the summation we will write as -1 plus 1 into V naught of S dash. So what is S dash here? When we'll take a left action from S4 state, we are going to be fall into the S4 state only. So we'll write V naught of S4 plus probability of taking right action from S4 state. The reward is -1 plus what is the change we are going to state transition towards right action from S4 to S5. So that will take us V0 of S5 plus, now we'll take upward action. So the probability of upward action from S4 state, the reward is -1. The transition, we are going to have right side S7 state, upside S2 state, downside S10 state. So we can write as, for all the actions, the probability of a particular action from state S6 summation, the probability of change of transition from S to S dash for a action A is 1, the reward is -1, discount factor is 1, and V naught of S dash. Depending upon the action, S dash will be changes. Again, here, what are the actions we are going to have? Left, right, upside, and downside. Now we will expand this. So the probability of action, that is left action from S6 state into -1 plus a V naught of, when we'll take the left side action, we are going to have the transition to S5 state plus the probability of right action from S6 state, the reward is -1, and V naught of, when we'll take right action, the change of transition is to S7 plus. Now we go for upward action from S6 state, -1 is the reward, and V naught of, when we are in S6 state and if we take upward action, we are going to transition to S2 state plus the probability of down action from S6 state, the reward is -1, V naught of, when we take downward action, what is the action? What is the state transition we are going to have? S10. As we know, the initial function, that is V naught of S for all the states, is equivalent to 0, and the probability of action, either it is left or right or upward or downward, the probability is 0.25 into -1 plus 0 plus 0.25 into -1 plus 0 plus 0.25 into -1 plus 0 plus 0.25 into -1 plus 0. Here we'll get as 0.25, I'll take as common. So left out is -1 plus 0, which is -1. Next also -1, -1, -1, which is going to give as 0.25 into -4, which will return -1. So now we will write V1 of S for V0 is, S0 is 0, S1 is -1, S2 is -1, S3 is -1, S4 is -1, S5 is -1, S6 we are updated with -1, S7, S8 till S14 and S15 they are 0. I am including the terminal states also. Now we will move to S7 state. So first iteration, so V1 of S7 state. When we are in S7 state, if you take a left action, we are going to be fall into S6. For right side, we don't have any more state, so we are going to be fall into the same state, that is S7. For upward action, the state is transit to S3. For downward, the state transit to S11. Now we will write the value function V1 for S7 state as summation of all the probability of actions from S7 state, summation of the transitions with a reward to S dash. The probability is we are considered as 1 and the reward is -1 and the discount factor is 1, multiply with the previous values, that is V0 of the change of transition depending upon the action. So now the various actions we can have is left, right, up, and downside. So by expansion of this left action from S7 state minus 1 plus V naught of. When we are take the left action, so we are going to have the next state is S6 plus phi of right action from S7 state. The reward is minus 1 V naught of. When we will take a right action, as we don't have any state on right hand side, so we are going to be fall into the same state S7 plus phi of upward action from S7 state. The reward is minus 1. The next state which we are going to have the transit for upward action from S7 is S3 state. So V naught of S3 plus the probability for the action toward downside from S7 state. The reward is minus 1. The state is transit to S11. So that is S V naught of S11. As the initial V naught for all the states as 0 and the probability of all the action is 0.25 or 1 by 4. So I'm taking 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0 plus 0.2 0.25 into minus 1 plus 0. Now, if you take 0.25 as common factor, 0.25 into minus 1 plus 0, minus 1 plus 0, minus 1 plus 0, minus 1 plus 0, which is going to give as 0.25 into minus 4, which will give minus 1. Now, the value function V1 for all the states are updated as V0, 0, V1, V2, minus 1, V3, minus 1, V4, minus 1, V5, minus 1, V6, minus 7, minus 1, V7, S7, we are considered as minus 1, for S8, for S9, S10, till S14 and 15 are 0. So the value function from S0 to S15 states we are updated. Now we will move to the next state, that is S8. The value function V1 of S8, which is equivalent to sum of all the actions, the probability of actions in S8 state, summation S dash comma R. The probability of transition from S to S dash is 1, multiply with reward is minus 1, plus discount factor is 1. So V0, as we are considering V1, we are going to take the previous value is V0 of the new state depending upon the action, that is S dash. Now we will expand for all the actions which are left, right, upward and downward. So which is equivalent to pi of action towards left side from S side. When we are in S side state, when we take the action towards left side, as we don't have any actions on left hand side, any states are on the left hand side, we are going to be fall into the same state. For right action, the transition is to S9. For upward, the state transition is S4. For downside, the state transition is S1. So we can write the probability of left action from S side multiply with reward minus 1 plus V naught of. When we take left action, we are going to be fall into the same state, that is S side plus the next action, the probability of action, that is right action from state S8, reward is minus 1 plus V naught of. When we take right action, the next state is S9 plus the probability for the action towards upside from S8 state, the reward is -1 plus V naught of, for S side, the upward action is towards S4 plus the probability of down action from S side state, the reward is -1 plus V naught of, when we take the down action, we are reaching to S12 state, that is S12. As V naught of all the states are equivalent to 0 and the probability is 0.25 for all the actions. So this equation is reduced to 0.25 into -1 plus 0 plus 0.25 into -1 plus 0 plus 0.25 into -1 plus 0 plus 0.25 into -1 plus 0. So this will use as 0.25. If you take common, left out is -1, -1, -1, -1, which is equivalent to 0.25 into -4, which is equivalent to -1. Now the value function V1 for all the states we will write as a list. For S0 state 0, for S1 minus 1, S2 minus 1, S3 minus 1, S4 minus 1, S5 minus 1, S6 minus 1, S7 minus 1, S8 minus 1. The remaining all are, we are not updated. So just I am putting the previous values only, which is zeros. Now we go to the next state, which is state S9. So here, whatever the calculation which you are done for 5, the same thing you can apply for S4, only the changes will be the state transitions. So for left side, we are going to have S8 state from S9, for right action S10, for upward S5, for downside S30. So the value function V1 for S9 state is equivalent to sum of all the action, the probability for the action A from state S9 summation. This probability is equivalent to 1 plus reward is -1, discount factor is 1, and the state of transition to S dash depending upon the action. So as we are having only one transition, this summation will have only one term. And for these actions, we have 4 actions, that is left side, right side, upside, and downside. Now we'll expand the probability of left action from S9 state, -1 reward plus V naught of, when we take the left action, the next state is S8 plus the probability of right action from S9, the reward is -1 and V naught. So when you take right action, the transition is to S10 plus pi of the probability of up action from S9 with a reward of -1 plus V naught of. When we take up action, the transition state is S5 plus pi of down action from S9 state. The reward is -1 and V naught of, when you take down action, the change of transition to S13 state. As we know, the probability of each action is 0.25 and the next state transition, that is V naught, is always 0, as we are initialized every state with a 0 value. Now we will substitute in this expression. So this will be reduced to 0.25 into -1 plus 0 plus 0.25 into -1 plus 0 plus 0.25 into -1 plus 0 plus 0.25 into -1 plus 0. Now if we take 0.25 as common factor, this expression we can rewrite as 0.25 into -1, -1, -1, -1, which will use as 0.25 into -4, which will reduce us to -1. Now we'll update the value function for all the state for the first iteration, that is V1 of S is equivalent to, for S0, 0, S1 minus 1, S2 minus 1, S3 minus 1, S4 minus 1, S5 minus 1, S6 minus 1, S7 minus 1, S8 minus 1, S9 we got as minus 1. Still we need to evaluate remaining function that I am taking as default as 0 now. Now we will move to S10 state. Now we are going to calculate the value function V1 for S10 state. When we are in S10 state, if you take left action, we are moving to S9 state. If it is right action, moving to S11 state. If it is upward, S6 state. If it is downwards, S14 state. Now this we can rewrite as summation of all the actions, the probability of the action whichever we are taking from the state S10, summation S dash R, the probability is 1, reward is minus 1, discount factor is 1. The next state transition that will write as S dash because it will vary with respect to the actions. So we will write as S dash now. In the expansion, we will write in detail. So the actions which we can take as left, right, up and down. So this we can write as the probability of left action from S10. The reward is minus 1 plus V naught of. So from S10 state, when you take the action towards left side, we are going to reach to S9 state. So write as V naught of S9 plus the probability of right action from S10 state. The reward is minus 1 V naught of. So when you take a right action from S10, we are reaching to S11 state plus the probability of up action from S10 state. Reward is minus 1. The change of state when you take upward action from S10, the next state is S6 plus the probability of down action from S10 state. The reward is minus 1 V naught of. So when you take downward action, so we are reaching to S14, S14. As we know, the probability of all the actions are 0.25 and the initial value that is V naught for all the states are 0. So by substituting this, we can rewrite the expression as 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0. 0.25 if you take as common, so you can write it as 0.25 into minus 1, minus 1, minus 1, minus 1, which is equivalent to 0.25 into minus 4, which will use minus 1. So the updated value function V1 of all the states, that is V1 of S, we can write as for S0 state is minus 0, for S1 minus 1, S2 minus 1, S3 minus 1, S4 minus 1, S5 minus 1, S6 minus 1, S7 minus 1, S8 minus 1, S9 minus 1, S10 updated to minus 1. Remaining states we are not evaluated, just I am taking as zeros. Now we will evaluate for S11 state. So the value function V1 for S11 state now we will find. So V1 of S11. So when we are in S11 state, for left action, we are moving to S0 state. For right action, as we don't have any state, we are going to be fall to S11 state only. For up action, S7 state. For down action, S15 state. It is a terminal state. The state value is by default it is 0. So now we will write the value function V1 for S11 state as summation of all the actions, the probability of action A in S11 state, summation S dash R, the probability we take as 1, reward is minus 1, discount factor is 1. So V0 of S dash. Depending upon the action, the next state will be changes. Now expanding this, as we know, the actions we can take is left, right, up, and down. So we can write the probability of left action from S11 state minus 1 plus V naught of. When we are in S11 state, the left action, the transition is to S10 state plus the probability of right action from S11 state, reward is minus 1, V naught of. When we take the right action, so we are going to be fall to the same state, that is S11 only, plus the probability of up action from S11 state, reward is minus 1, plus S naught of upward state. When you take upward action, we are going to have the transition to S7 plus the probability of down action from S11 state. The reward is minus 1 plus a V naught of. So when we take down action, we are moving to the terminal state S50. As V naught is 0, all the cases, and the probability is for all the action is 0.25, substituting the value 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0, which is equivalent to, I'll take 0.25 as common factor. So the left out values are minus 1, minus 1, minus 1, minus 1, which will give us as 0.25 into minus 4, which is minus 1. Now the updated, the value function v1 for S state S, we can write as for S0 state 0, S1 and S1, S2 minus 2, S3 minus 1, S4 minus 1, S5 minus 1, S6 minus 1, S7 minus 1, S8 minus 1, S9 minus 1, S10 minus 1, S11 we are updated as minus 1. The remaining we are not evaluated, just I am taking as zeros. Actually, it should be empty space. Now we will go for S12 state. Now we will find out the value function V1 for S12 state. So that we will write as a V1 of S12. So when we are in S12 state, if we take left action, we are falling into the same state. For right action, S13 state. For upward, S8 state. For downside, we don't have any state, so we are going to be fall into same state. This is down. So the value function we can write as sum of all action, the probability of a particular action from S12 state, summation of S dash R, the probability of state transition we are considered as 1, the reward is minus 1, plus discount factor is 1, Vk of S dash. So that we will write as a V naught of S dash. Depending upon the action, S dash will be changes. So here the actions we can have is left, right, up, down. So the expansion we can write as the probability of left action from S12 state into minus 1 plus V naught of. When we take a left action, we are going to be fall into the same state, that will write as S12 plus the probability of a right action from S12 state with a reward of minus 1 plus V naught of. When we take a right action, we are going to be fall to S13 state plus the next action, that is upward side from S12 state, reward is minus 1 plus V naught of. When you take upward action from S12 state, the next state is S8 plus pi of down action from S12, which is going to be reward is minus 1 plus V naught of. So for downside, we don't have any state, so it will be fall to the same state. So that will take as S12 state only. As we know, the probability of each action from the state is 0.25 and the initial value V naught for any state is equivalent to 0. Substituting that, you get as 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0. Now here we will take 0.25 as common. Then we can rewrite the expression as 0.25 into minus 1, minus 1, minus 1, minus 1, which will rise to 0.25 into minus 4, which is equivalent to minus 1. So now the updated value function v1 of s we can write as for s0, 0, S1 minus 1, S2 minus 1, S3 minus 1, S4 minus 1, S5 minus 1, S6 minus 1, S7 minus 1, S8 minus 1, S9 minus 1, S10 minus 1, S11 minus 1, S12 minus 1. The remaining will take as 13, 14, 15 as zeros. Now we will move to S13 state for finding out the value function. So that we will write as V1 of S13 when we are in S13 state. Now if we take left action, we fall into S12 state. For right action, S14 state. For up action, S9 state. For down action, we are going to be fall into the same state as we don't have any more state on the downside. So now the value function for S13, that is V1 of S13, we can write as summation of all the actions, probability of a particular action from state S13, summation of S dash R, the probability of transition from state to state is 1, reward is minus 1, discount factor is 0, discount factor is 1, and V naught of the next state depending upon the action. Here the actions which we are going to be considered as left, right, up, down. So now we can expand as the probability of left action from S13 state into minus 1 plus a V naught of. So when we take left action, the next state is S12. So V naught of S12 plus the probability of right action from S13 state. The discount is reward is minus 1 plus V naught into when you take right action, you are going to be change the transition to S14 state plus the probability of up action from S13 state minus 1 reward plus V naught of when you take up action, the next state is S9 plus the probability of down action from S13 into minus 1 is the reward plus V naught of when we take the down action, we are going to be fall into the same state, that is S13. So as the probability of any action is 0.25 and V naught for any state is 0, by substituting the values, we can rewrite the function as 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0 plus 0.25 into minus 1 plus 0. If we take 0.25 as common, so what is left out by adding minus 1 plus 0, minus 1, minus 1, minus 1, minus 1, which will give us 0.25 into minus 4, which is equivalent to minus 1. Now the value function V1 for all the states that we can write as V1 of S for S0 state 0, for S1 V1, S2 V1, S3 V1, S4, S5, S6, S7, S8, S9, S10, S11, S12, S13 is minus 1, 14 we have to evaluate it. However, 15 is 0. Now we will take the value function for state S14, that we can write as a V1 of S14. Now when we are in S14 state, if you take left action, the next state is S13. For right action, S15, which is nothing but a terminal state. For up action, S10. For down action, will fall into the same state. So now we will write the value function for S14 as V1 of S14 is equivalent to summation of all the actions, the probability of particular action A from the state S14 into summation of S dash R. The probability of any transition from S to S dash is 1. The reward is -1, discount factor is 1, a V naught of the next state depending upon the action. So that we can write as we know, the actions which we can take as a left, right, up, and down. Now, by expanding this, the probability of left action from S14 state -1 plus V naught of when we'll take the left action from S14 state, the next state is equivalent to S13 plus pi of right action from S14 state -1 is the reward. V naught of when we will take the right action, the state is transit to the terminal state. So instead of S15, I'll write as ST, that is terminal state, plus the probability of up action from S14 state, the reward is -1. So when you take up action from S14, the next state is S10. So we write as V naught of S10 plus the probability of down action from S14 state -1 plus V naught of when you take the downside, the transition is falls to the same state, that is S14. Again, the probability of all actions from any state is 0.25 and V naught of any state is equivalent to 0. By substituting those values, we can rewrite the function as 0.25 into -1 plus 0 plus 0.25 into -1 plus 0 plus 0.25 into -1 plus 0 plus 0.25 into -1 plus 0. Now we will take 0.25 as common factor. So by adding -1 plus 0, we'll get as -1, -1, -1, -1, which is equivalent to 0.25 into -4, which will use as -1. Now the value function for all the state S. Now we are evaluated for all the states. Terminal states we are not going to evaluate because the value function for the terminal state is always 0. S1, S2, S3, S4, S5, S6, S7, S8, S9, S10, S11, S12, S13, S14, and the terminal state is 0. Now this is one iteration we have done. So like this we have to iterate the state transitions for all the states until from one state to another state the value function should not alter, because there we are going to get the optimal value function. Now we'll go to the second iteration. So now in this case, at this point, I'll write the states as for previous and after values we are going to be considered here. So this is for V naught, and the same thing I'll update for V1 also. So what we have here, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So these are the initial values which we are considered, and the new evaluated values are -1 except the terminal states. So this is 0. Here we have -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, 0. So this is the value function after first iteration. So this I'll give the label as V naught, V naught of S, and this is V1 of S. So we have done one iteration. Now we will move to the second iteration. So this is for states. I'm considering this box, and this is the previous. This is a V1. Now we are going to evaluate for a V2. So where we are going to be update a V2 on the downside. So for this one also I'll put set a table columns S02, S15, 16 columns and 2 rows. Okay. Now we'll find out the value function, which is V2, because we are evaluated previously V1. Now we will move to the value function, which is a V2. Now we will write, again we will start from S1 state. So remember here the terminal states, which are S0 state and S1 S15 state, no need to evaluate, because for all the terminal states the value function for any iteration they are equivalent to 0. Now we want to update from S1 to S14. Now we will see with respect to uh, iteration 2 for S1 state. Straight away I am writing summation of phi A from S1 state. The probability is 1. The reward is -1. Discount factor is 1. So straight away I am writing 1 plus Now here k plus 1 is equivalent to 2. Now we will take this one as a v1 of s dash. So for left action, so pi of left from s1 state minus 1 plus a v1 of, so which state we are going to consider if it is in left side. So now we are in s1 state. So the left action is s0 state plus pi of right action from s1 state minus 1 plus v naught of, when we'll take the right action, we are moving into s2 state plus pi of up action from s1 state. So when we take up action, we are going to be fall into the same state. So minus 1 plus a v1 of s1 state plus pi of down action from s1 state minus 1 plus v naught. So when we take down action, we are going to be fall to s1 state. So now which is equivalent to the pi of all action is 0.25. So 0.25 into minus 1. So what is v1 of S naught? V1 of S naught is 0. So plus 0 plus 0.25 into minus 1. V1 of S2. So what is V1 of S2? So this is S1, S0, S2, and this is S5. Now we are going to find this value as minus 1 plus 0.25 into minus 1. So V naught of V1 of S1. So V1 of S1 is minus 1 plus 0.25 into minus 1. So what is V1 of S5? Which is minus 1. Now we can rewrite this function as 0.25 into minus 1 plus 0. Minus 1, minus 1, minus 1, that is minus 2. Minus 1, minus 1, that is minus 2. Minus 1, minus 1, minus 2, which is going to give as 0.25 into minus 7. Now we are going to find out the product of 0.25 into 7, that is minus 7. So which is going to give as 1.75. So this I'll write as minus 1.7. So for S1 state, what is the updated value? Here we got this one as minus 1.75. Next we will evaluate for S1 state. So the value function for S2 state we are going to evaluate. S1 state already we are evaluated. This is minus 1.75. Now we will write V2 of S2. So for S2, left action is S1 state, right action is S3 state, up action is S2 only, down action is S6. So this we can write as summation of all the actions, the probability of action A from state S2. The probability here is 1, reward is minus 1, discount factor is 1. So straight away I am substituting as minus 1 plus what is Vk? Vk is now V1 depending upon the action S dash. So expanding this, pi of left action from S2 state minus 1 plus V1 of S1, because in S2 state the left is S1 plus pi of right action from S2 state. So right action, the next transition is S3 state. So you write as minus 1 plus V1 of S3 plus pi of up action from S2 state. So when you go for up state, we are going to be fall into the same state. So that will write as S2 state. Pi of down action from S2 state. So when you take down action, the transition is for S6 state. So V1 of S6. Here we can see here, this is S2, V1 of S1, V1 of S3, and V1 of S6. So what is the value we can write? For all the actions from any state, the probability is equal to 0.25 into, now we'll substitute the V1 values. Now if you observe a V1 of S1, S3, S2 and S6, for all these four cases, the value is -1. So straight away you can write -1 plus 0.25 into -1 plus 0.25 into -1 plus 0.25 into -1, which we can rewrite as 0.25 if we take as common, -1 and do as -2, -1 -1 -2, -1 -1 -2, -1 -1 -2. How much you get? -2 -2 -2 -2, that is -8. So 0.25 into -8, which we are going to get as minus. Now we will update S2 as -2. Now we will move for S3 state. The value function which we are going to consider is a V2. So V2 of S3 we are going to calculate. Previously we have considered the terminal states with the value function is always zeros. S1 we are evaluated -1.75, S2 as -2. Now we are going to evaluate for S3 state. So for S3 state, the left action is S2, right action is S3, upward is also S3, downward is S7. Now we will write summation of all the actions, the probability of the particular action A from S3 state. This probability we are assumed as 1, reward -1, discount we are considered as 1. So we can write this one as -1 plus Vk. What is the k value? That is V1 of S dash depending upon the action. So now this will expand. As we know, the actions are left, right, up and down. I'll write the probability of left action from S3 state -1 plus V1 of, for left action from S3 state, we are going to have the next state is equivalent to S2 state plus the probability of right action from S3 state. The reward is -1 or V1 of, when you take right action, we are going to be fall to the same state, that is S3 plus the probability of up action from S3 state. So when you take the up action from S3 state, we are going to be fall into the same state, that is reward is -1 plus V1 of the same state is, that is S3 plus pi of the probability of down action from S3 state, -1 is the reward. So when you take down action, the next state is S7. So you write S7. Substituting, as we are considered equal probable for all the actions. Now I'll take this one as 0.25 into -1. So now when you are in S3 state, what are the next states we are going to be considered? V1 of S2 value is required, V1 of S3 value and V1 of S7. So V1 of S2, S3, S7 are -1. So straight away you can write as 0.25 into -1 plus 0.25 into -1 plus 0.25 into -1 plus 0.25 into -1. If you take 0.25 as common factor, so what is left out? -2, -2, -2, -2, which it is going to give as 0.25 into -8, which will give us -2. Now we will update S2 with -2. Now we go for evaluating S4. So the value function for second iteration, that will write as a V2 for S4. Now when we are in S4 state, the left action will be false to S4 only, right action S5 state, upward action S0 state, the downward action S8 state. Previously, we have computed S1 state as minus 1.75, S2 as minus 2, S3 is minus 2. The terminal states are zeros. Now we will see V2 of S4, which is equivalent to summation of all the actions, the probability of particular action from S4 state. This probability of state transition we are considered as 1. Reward is minus 1. Discount factor is 1. So you can write function as minus 1 plus V1 of S dash, where S dash will depend upon the action which you are going to be considering. So by expanding this for all the actions, so the probability of left action from S4 state minus 1 plus V1 of, so when you take the left action from S4 state, we are going to be fall into the same state, that is S4 plus the probability of right action from S4 state, reward is minus 1, V1 of, when we take right action, we are going to change the state to S5, so here we get as S5 plus the probability of up action from S4 state minus 1 plus V1. So what is the up action? When you are in S4 state, when you take up action, we are going to be fall to the next state is equivalent to S0 plus pi of down action from S4 state. The reward is minus 1 plus V1 of. When you take the down action, so what is the state we are going to have the transition to S side? So V1 of S side. So for finding out this function value, what we require here it is a V1 of S4. This is S4, S0, this is S5, and this is S side. Now, if you observe the cases, the value functions for V1 of S4 is minus 1 and the V1 of S5 is minus 1, V1 of S0 is 0, V1 of S8 is minus 1. By substituting these values, we can write as 0.25 into minus 1. So V1 of S4, V1 of S4 is minus 1 plus the probability is 0.25 minus V1 of S5. So what is V1 of S5? Which is equivalent to minus 1. Next, the probability is 0.25 for up action minus 1 V1 of S0. Now, if you observe V1 of S0 is equivalent to 0, substitute this one as 0 plus 0.25 into minus 1 V1 of S8. So, what is V1 of S8? V1 of S8 is equivalent to minus 1. So, this will get as minus 1. Now take 0.25 as common factor. What is left out? Minus 1, which is equivalent to minus 2. Minus 1, which is equivalent to minus 2. Minus 1 minus 0, minus 1. Minus 1 minus 1, minus 2. Which will give us as 0.25 into minus 7. So when we find 0.25 into minus 7, which is going to give us minus 1.75. So for S4 state, we will get the value as minus 1.75. Now we will move to S5 state. The value function of V2 for S5 state. Before finding this, I am updating the V2 function which you have calculated. So S1 is minus 1.75, S2 is minus 2, S3 is minus 2, S4 is minus 1.75. Now we are interested to find out V2 for S5 state. Now when you are in S5 state, left action changes to S4, right action to S6, up action to S1, down action to S9. Now we will write this one as value function as summation of all the actions, the probability of actions from S5 state, the probability of change of transition from state to state is 1, a reward is minus 1, and the discount factor is 1. So we can write as minus 1 plus V1 of S dash depending upon the action. This S dash will be changes. Now various actions we are having left, right, up and down. So now we will expand this. The probability of left action from S5 state minus 1 plus V1 of, when you take left action, the next state is equivalent to S4 plus the probability of right action from S5 state with the reward is minus 1 plus when we take the right action from S5, we are reaching to S6 state. So the next state is S6 plus the probability of up action from S5 state minus 1 is the reward. So what is the next state? It is going to have the transition. When you take up action, the next state is equivalent to S1 plus pi of a down action from S5 state minus 1 is the reward V1 of. So when we are in S5 state, if you take down action, we are taking S9 state. So which is equivalent to the probability of all the actions is 0.25. Here we require V1 of S4. So V1 of S4 is minus 1 and V1 of S6 is required, that is minus 1. V1 of S1 is minus 1. V1 of S9 is minus 1. So substituting these values, we'll get minus 0.25 into minus 1 plus 0.25 into minus 1 plus 0.25 into minus 1 plus 0.25 into minus 1. Now, if you take 0.25 as common factor, minus 1, minus 2, this minus 1, minus 2, minus 1, minus 2, minus 1, minus 2. So, which it is going to give as 0.25 into minus 8, which is gives us minus 2. So, the S5 value we got as minus 2. Now, we will evaluate the value function V2 for S6 function. So before evaluating the value function, now I will update the previously considered as well as evaluated the state values, that is for S1 minus 1.2, 1.75, S2 is minus 2, S3 is minus 2, S4 is minus 1.75, S5 we are evaluated is minus 2. Now we are going to evaluate this S6. So now we will write a V2 of S6. So the value function for the state S6 we will write as a V2 of S6. Now when we are in S6, left action will falls to S5, right action changes to S7 state, up action next state is S2, for down action the next state is S10. So now we will write the value function as summation of all the actions, the probability of a particular action in S6 state, the probability of state transition is 1, the reward is minus 1, and the discount factor is 1. So now by substituting this, you get as minus 1 plus V1 of S dash, where S dash will be changes with respect to action. Now the various actions we are having is left, right, up, down. So we'll write the probability of left action from S6 minus 1 is the reward plus V1 of S6 to left action is S5. So V1 of S5 plus the probability of right action from S6 state minus 1 is the reward plus V1 of, when we take right action, we are going to change the transition to S7 state plus the probability of up action from S6 state minus 1 is the reward V1 of, when we'll take up action, we are changing the state to S2. So V1 of S2 plus pi of down action from S6 state. The reward is minus 1 V1 of. When we take the down action, we are changing the next state to S10. So V1 of S10. As we are considered the probability at 0.25, and here we require the V1 of S5, V1 of S7, and V1 of S2 and V1 of S10. So as S2, S5, S7, S7 are minus 1, so what we can write? 0.25 into minus 1 plus 0.25 into minus 1 plus 0.25 into minus 1 plus 0.25 into minus 1 minus 1. Now if you take 0.25 as common factor, minus 1 into minus 1, that is minus 2, minus 2, minus 2, here also minus 2, which is equivalent to 0.25 into minus 8, which is going to give rise to minus 2. So S6 value is also minus 2. Now we will find out for S7, we will find out the value function. V1 we are evaluated, a V2 of S7. Before that, I will update the V2 whichever we are computed and assume S0 is equivalent to the terminal states will have the value function is 0. S1 we got as minus 1.75, S2 is minus 2, S3 is minus 2, and S4 is minus 1.75, and S5 we are evaluated is minus 2. For S6 is also minus 2. Now we are going to evaluate it to S7. Now when we are in S7 state, if you take left action, the next state is X6. If it is right action, next state is S7. Up action, the next state is S3. For down action, the next state is S11. So now we will write this value function V2 of S7 as summation of all the actions, the probability of actions from S7 state, the probability of change of transition from state to state is 1. The reward is minus 1. Discount factor is 1. So we can write as minus 1 plus V1 of S dash, where S dash will depend upon the action. Now we will expand for all the 4 actions, so that we can write as the probability of left action from S7 minus 1 is the reward V1. So what is the next state for S7 for left action, which is equivalent to S6 plus the probability of right action from S7 state. The reward is minus 1, and V1. When you take right action, we are going to be fall to the same state, that is S7, plus the probability of up action from S7 state. Minus 1 is the reward V1 of from S7. If you take up action, the next state is S3 plus Y of down action for S7 state. So when you take down action from S7 state, the next state is S11. So you write V1 of S11. So for computing this V2 of S7, what are the values we require? We require V1 of S6, V1 of S7, V1 of S3, and V1 of S11. Now if you observe, all the 4 values are minus 1. So already we are computed the same kind of cases. So you can write 0.25 into minus 1 minus 1 plus 0.25 into minus 1 minus 1 plus 0.25 into minus 1 minus 1 plus 0.25 into minus 1 minus 1. If you take 0.25 as common factor, minus 2, minus 2, minus 2, minus 2, which we can rewrite as 0.25 into minus 8, which will gives rise to minus 2. Now we will update S7 with minus 2 for the value function V2. So V2 of S7 we got as minus 2. Now we will compute for S8. So the value function V2 for the state S8 we will write as a V2 of S8. When we are in S8 state, the left action will be false to S8 only. Right action changes to S9. Up action changes to state is S4. For the down action, the change of state is S12. So this we can write as summation of all the actions, the probability of actions in S8 state, the probability of change of transition from state to state is 1, reward is minus 1, discount factor is 1. So this we can write as minus 1 plus V1 of S dash, where S dash will depend upon the action. So as we know, four actions we can consider. So the summation we can expand as the probability of left action from S8 into minus 1 plus V1 of. So for left action from S8, we are going to be fall to the same state S8 plus the probability of right action from S8 state multiply with minus 1 plus V1. So when you take a right action, so we are going to reach to S9 state. So V1 of S9 plus pi of up action from S8 state. Reward is minus 1 V1 of. When you take up action from S8, we are reaching to S4 state. So we'll get a V1 of S4 plus pi of down action from S8 state. Reward is minus 1 V1 of. When you take down action, we are going to be change the state to S1. So the probability of any action is 0.25, and here we require V1 of S8 which is equivalent to minus 1, S9 which is equivalent to minus 1, S4 which is equivalent to minus 1, S12 which is equivalent to minus 12. So this we can rewrite as 0.25 into minus 1 plus 0.25 into minus 1 plus 0.25 into minus 1 plus 0.25 into minus 1, which will give us to 0.25 into minus 8, which will give us to minus 2. So what is the updated V2? S0 is 0, S1 is minus 1.75, S2 is minus 2, S3 is minus 2, S4 is minus 1.75, S5 is minus 2, S6 is minus 2, S7 is minus 2, S8 is also minus 2. And however, S15 is 0 as it is a terminal state. Now we go for finding out S9, S10. So now if you observe for S9, S10, so all the four states on all these sides are 1, 1. For S9 also all these four are 9, 9. So I am skipping S9 and S10. So this also will get as minus 2 and minus 2. So here you can compute similarly for value function V2, that is for S9 and V2 of S10. Now we will go to S11. Now we will calculate the value function of V2 for S11. So here I'll write a V2 of S11. So when we are in S11, if you take a left action, we are going to be change the state to S10, a right action to S11 only, up action to S7, the down action is the terminal state. So now we will write the value function for S11 as summation of all the actions, the probability of action A from S11 state. The probability of state transition is 1, reward is minus 1, discount factor is 1. So this we can write as minus 1 plus V1 of S dash, where S dash will depend upon the action. So now we can expand this one as the probability of left action from S11 minus 1 plus V1 of, for S11 the left action is S10. The probability of right action from S11 state, the next state we are going to get is V1 of. So for right state, we are going to be fall to the same state. This is equivalent to S11 plus the probability of up action from S11. So when you take the up action from S11, we are going to be change the state to S7. So that is V1 of S7. Probability of down action from S11 state, minus 1 is the reward, V1 of. So what is the next state you will get for down action, which is equivalent to S15 or terminal state. Now for V1, calculating V2 of S11, what we require? S10 we require. So the V1 of S10 is minus 1, V1 of S11 is minus 1, V1 of S7 is minus 1, and V1 of the terminal state or S15 is equivalent to 0. Substituting, the probability distribution for all the action is 0.25 minus 1. So V1 of S10 is minus 1 plus 0.25 into minus 1 into V1 of S11 is minus 1 plus the probability is 0.25 into minus V1 of S7 is minus 1 plus 0.25 into minus 1 V1 of S15 is 0. Now take 0.25 as common factor, minus 1 will get as minus 2, minus 1 which is equivalent to minus 2, minus 1 which is equivalent to minus 2, minus 1 plus 0 which is equivalent to minus 1. So which is gives to 0.25 into minus 7. So take 0.25 into minus 7 will get which is equivalent to minus 1.75. Now we will update V2. As we know, the terminal states are 0. The S1 is equivalent to minus 1.75, which we are evaluated. S2 minus 2, S3 minus 2, S4 minus 1.75, S5 minus 2, S6 minus 2, S7 minus 2, S8 minus 2, S9 minus 2, S10 minus 2, S11 we got minus 1.75. Now we go for evaluating S12. So now we will evaluate the value function for that is V2 of S12. Before that, I will update the evaluated till now, that is V2, S0 is 0, S15 is 0, S1 is minus 1.75, S2 is minus 2, S3 is minus 2, S4 is minus 1.75, S5 is minus 2, S6 is minus 2, S7 is minus 2, S8 is minus 2, S9 is minus 2, S10 is minus 2, S11 is minus 1.75. Now we are going to evaluate for S1. So for S12, when we take left action, we are going to be fall to the same state. Right action S13, up action S8, down action S12. Now this we can write as summation of all actions, the probability of action A from S12 state. The state transition probability is 1, reward is minus 1, discount factor is 1. So we can rewrite this one as minus 1 plus V1 of S dash, where S dash will depend upon the action. So the actions we can take 4 here. So now expanding this, the probability of left action from S12 minus 1 plus V1 of. When we take left action from S12, we are going to be fall into the same state, that is S12 plus the probability of right action from S12 state, reward is minus 1, V1 of. What is the next state we are going to have? S13 plus the probability of up action from S12 state, minus 1 plus V1 of. For S12 up action, the next state is equivalent to S8 plus the probability of down action from S12 state, the reward is minus 1. The V1 of, when you take down action, we are going to be fall to the S12 state only. So for computing this V2 of S12, what are the values we require? V1 of S12 we require, V1 of S13, V1 of S12 and V1 of S8. So substituting the values, you'll get 0.25 into minus 1. So here all the 4 values are minus 1 only. So straight away I am substituting 0.25 minus 1 plus 0.25 into minus 1 plus 0.25 into minus 1 plus 0.25 into minus 1, which is equivalent to, if you take 0.25 as common, minus 1 minus 2 minus 1 minus 2 minus 1 minus 2 minus 1 minus 2. which is equivalent to 0.25 into minus 2 minus 2 minus 2 minus 2, which will use as minus 8, which will use as minus 2. Now we will update S12 as minus 2. Now we go for computing V2 of S13. So the value function of V2 for S13 state, that we will write as V2 of S13. When you are in S13, left action S12, right action S14, up action S9, down action, we are going to be fall into the same state, that is S13. So now we will update already computed values. Terminal states are zeros. S1 is minus 1.75, S2 is minus 2, S3 is minus 2, S4 is minus 1.75, S5 is equivalent to minus 2, S6 is equivalent to minus 2, S7 is equivalent to minus 2, S8 is equivalent to minus 2, S9 is equivalent to minus 2, S10 is equivalent to minus 2, S11 we got as 1.75, again S12 is equivalent to minus 2. Now we are going to evaluate S13. So how we can write V2 of S13 is equivalent to summation of all the actions, the probability of actions from S13 state. State transition probability is 1, reward is minus 1, discount factor is 1. So which is equivalent to minus 1 plus V1 of S dash, where S dash will depend upon the action. So now by expanding this for all the actions which are left, right, up and down, we can write the probability of left action from S13 state minus 1 plus V1 of, when you take the left action from S13 state, the next state is equivalent to S12 plus the probability of right action from S13 state, reward is minus 1, V1 of, when you take a right action, we are going to be change the state to S14 plus the probability of up action from S13 state. When you take up action from S13 state, we are reaching to S9 state. So minus 1 plus V1 of S9 plus the probability of down action from S13 state. So when you take the down action from S13 state, we are falling to the same state. So that is V1 of S13. So for computing V2 of S13, we require V1 of S12, V1 of S14, V1 of S9, and V1 of S13. Now, if you observe, all these four values are minus 1 and the probability of each action is 0.25. So, straight away I am writing 0.25 into minus 1 plus 0.25 into minus 1 plus 0.25 into minus 1 plus 0.25 into minus 8. It is minus 2. So S13 also we got as minus 2 value. Now we are interested to find out S14. So for S14, we will compute the value function, that is V2 of S14. When we are in S14 state, left action S13, right action terminal state, that is S15, up action S10 state, down action falling into the same state. Now we'll update the expression as V2 of S14 is equivalent to sum of all actions, the probability of action A in S14 state. The probability of state transition from S to S dash is 1, reward is minus 1, value function is 1. So we can write as minus 1 plus V1 of S dash, where S dash will depend upon the action. Now expanding for all the four actions, that is left, right, up and down, we can write as the probability of left action from S14 state minus 1 plus V1 now. When we'll take left action, the next state is equivalent to S13 plus the probability of right action from S14 state. So when you take the right action from S14 state, we are reaching to the terminal state, that is a V1 of S15 plus the probability of up action from S14, the reward is minus 1. So when you take the up action from S14 state, we are reaching to S10. So that you write as V1 of S10 plus the probability of down action from S14 state, the reward is minus 1, V1 of. So when you take the down action from S14 state, we are falling to the same state, that is S14. So when we are in S14, for finding out the value function for S14, V1 of S13 is required. Next, V1 of S15 is required. V1 of S10 is required. And V1 of S14 is required. Substituting, the probability of all the actions is 0.25 and V1 of values of the states, we will get 0.25 into minus 1. V1 of S13 is minus 1 plus 0.25 into minus 1. V1 of S15 is 0 plus 0.25 into minus 1. V1 of S10 is minus 1 plus the probability is 0.25 into minus 1. V1 of S14 is minus 1. Taking 0.25 as common factor, 0.25 minus 1, it will use as minus 2, minus 1 plus 0, minus 1, minus 1 minus 1, minus 2, minus 1 minus 1, minus 2, which is equivalent to 0.25 into minus 8. So which reduces us to, not minus 8, sorry, this is minus 7. So which is equivalent to minus 1.75. Now we will update the evaluated V2 functions. So the V2 functions we got as S0 is 0, S15 is 0, S1 is minus 1.75, S2 is minus 2, S3 is minus 2, S4 is minus 1.75, S5 is minus 2, S6 is minus 2, S7 is minus 2, S8 is also minus 2, S9 minus 2, S10 minus 2, S11 minus 1.75, S12 minus 2, S13 minus 2, S14 minus 1.75. So now we can proceed until what point we have to consider. So now we are evaluated two iterations. So initially we are considered the V0 as all the states will have the value is equivalent to 0. So the value function for the first iteration, that is initialized V0, we are considered as all zeros, right? Then we are evaluated V1 of S, where we got the terminals are 0 and the remaining elements are minus 1. And V2 of S, which is equivalent to 0, minus 1.75, 1, minus 2, minus 2, like this. We got some values and the terminal state is equivalent to 0. So until what point we have to consider? Here V3, V4, V5, until what point we have to consider is whenever we get a Vk plus 1, whenever the two consecutive iterations of value functions are going to give the same value, then we can stop. So that at that time we can consider it is a optimal value function which is equivalent to V star. Till that point we have to evaluate. So now the remaining cases I have tabulated. So this is all the iterations for S0 state to S15 state, where we have rounded this one to 4 decimals. When we go for calculation until 4 decimals, so where the convergence is taking place in 195 and 196 iterations, you can see for each and every state the values are same. So whenever you are getting all these state values are 0, then we can stop the iterations. So this is rounded as minus 14, minus 20, minus 22, minus 14, minus 18, minus 20, minus 20, minus 20, minus 20, minus 18, minus 14, minus 22, minus 20, minus 14, and 0. The same procedure, if you are rounded for 2 decimals, then we are going to get the convergence in 111 and 112 iterations. Previously, for 4 decimals, 195, 196 iterations are required for convergence, whereas for 2 decimals, if you round it, 111, 112 iterations, it is getting convergence. If you are rounded for 1 decimal, so we are going to get the convergence in 69th and 70th iterations. So this is the procedure for finding out the iterative policy evaluation in the small grid world. Thank you all.